Welcome. In this video I'll discuss Poisson brackets, which are an important component of reduced MHD models, and implementing them correctly in numerical methods is something that needs a bit of care because it has various conservation properties which can be very important to try and maintain. And I'll show some of the properties that we need and some of the properties that are broken when you implement them in a simple way numerically, and then one particular quite classic way of solving this problem, which is called Arrow brackets. And so we're going to start by showing how these Poisson brackets arise. And they're basically from either the Ecosphere advection terms or the compression terms. So anything with the curvature terms can be implemented also as Poisson brackets. And so we'll look at the Ecosphere terms. So you have the Ecosphere velocity, dotted with a gradient of some field, which could be density or vorticity particularly. But most terms in the reduced MHD models have terms like this. And you can write this as this is the Ecosphere velocity, so we have 1 over b, unit vector in the b direction crossed with the potential, dotted with this gradient of some field like density or vorticity. And it can be convenient to write this in field line coordinates. So this is where we have, so b can be written as the cross product of two quantities which are constant along magnetic fields. So grad x cross grad y, for example, so that b is in the z direction. We can then write this whole thing in terms of gradients of x, y, and z, and it's very useful to be able to write this. So we first write this b cross grad phi dot grad f. It's useful to rewrite this because there's just the triple product, and so we can just change this to be grad phi cross grad f dotted with b, and then to write phi, a gradient of phi, this part here, this is the potential in terms of its x, y, and z components, and the same for f. And then we can rewrite the Poisson bracket term as the following. So this first term, grad x cross grad y, that's of course just b. This term here, grad x cross grad z, is like ey. So this is like 1 over j ey, and this is just 1 over j ex. And so here we have terms which are typically small, and the most important term, and usually, well, quite often the only term that's kept is this first term here. And so what you can do is you can write this whole thing. So this has got a b in front of it here. So I've just written out this component here without the 1 over b. This is b times e. So this gives you a b dotted with the unit vector, of course just gives a b. And then the whole thing is often written, say, neglecting these terms here. So if you either assume that the coordinate system is orthogonal, or you assume that these terms are small, then quite often this whole thing is written as. So you see this is an anti-symmetric operator. So it has a derivatives in x and y, which are the two directions orthogonal to the magnetic field. And it's anti-symmetric, so you have d phi by dx, df by dy, and then with a sign flip with a d phi by dy, df by dx. And this is often written as a bracket, so phi f, and this is the Poisson bracket. So reduced MHD models are often written in terms of these brackets, and what they mean is just these anti-symmetric operators perpendicular to the magnetic field. So when we implement these models numerically, the choice of how we solve this can be quite important. And quite often one of the things we're interested in is conservation properties. So if you have a turbulent spectrum, for example, the conservation of energy and entropy can be quite important to getting the right spectrum. And so if we're solving, for example, density, we might be interested in conservation, making sure that density is conserved. And so you can write down, for example, a density equation. And in the case where it's incompressible, the Ecosphere direction just becomes this. So this is for incompressible flow. In which case, if you want the density to be conserved, then we need that the integral over the whole volume of this is equal to 0. And one way of seeing this is to just write this term here. So we have this Poisson bracket, it's just 1 over b cross grad and just write this as a divergence. There's often the trick with conservation properties is to turn everything into a divergence, and then when you integrate over the volume you just get a surface term. So here I've just turned this into the divergence, the ecos b flow minus the compression term, and of course that's 0 because it's incompressible. And so now if we integrate this over the volume, and we want that to be equal to 0 if there are no boundary fluxes. And so if we look at what properties this therefore needs to have, we therefore need the integral of this over the volume should be equal to 0, so if no boundary flux. And so different choices of implementations, if you calculate this numerically, this becomes a sum. So you have basically a sum over all your grid cells of this term phi n evaluated at each grid cell, and it's sum over say the volume of the cell, so delta v, like the volume of each cell. That should be equal to 0 if you sum over your whole grid. This is like the discrete form of this conservation law. For vorticity, there's another important conserved quantity, which is the entropy, which is the square of the vorticity. And you can see this by writing this vorticity equation. So if I have a simple vorticity equation, so with no drive terms here, so this is just vorticity and scalar potential. And here I'm just solving that for example, you have like vorticity is the Poisson equation applied to the potential. So if we multiply this equation through by omega, so we have an omega d omega by dt. And so this term here, so you just get half omega squared from there, and then this term also we can just use the same divergence form and just write that this is just a half divergence of omega squared. So we have here the divergence of flow, and again this is incompressible. So I assume that the compression of this term is 0. And so here this just says that again omega squared is also a conserved quantity. This is an equation just like the one for the density. So we can turn this into an equation for a numerical equation. So when you choose some way of implementing this, what we'll have is if you have say a two-dimensional grid, so a 2D grid with cells I and j, so say in the x and the y direction. What we have is the sum of the entropy, so we have basically the sum over I and j, so the x and the y directions. Say the omega term times this phi omega at this location I, j, this is I and j. So we need to evaluate what this is numerically, and then this whole thing summed over the whole domain should be equal to 0. So we should have the sum of the rate change of time of omega squared plus the sum over all the grid cells of this should be equal to 0. It's just a discrete form. So if we of the conservation equations. And so if you have a time-dependent independent system, so if omega squared here is not changing, then we should be able to find that this should be equal to 0. So this should be it equals 0 if there's no time dependence. So what we find is that different ways of solving this equation, or different ways of discretizing this equation, turning it into a numerical method, will give different results. So a simple way of doing this would be if you were just to write sort of second order central difference so writing down, say, d5 by dx at a location ij would be roughly equal to phi so we have the position at the next index in x minus position at the last index in x. So this is I minus 1 and j divided by 2, say delta x. That would be a second derivative in x. And so we can write down the Poisson brackets. And so here we have the d phi by dx times d omega by dy minus d phi by dy times d omega by dx. And then we can look at this equation and you can see which terms we need to cancel out. So if you multiply this term by, say, omega ij, what you end up with is a term with omega I j plus 1, and the terms basically with all the omegas at each point nearby. But here we have omega I times j plus 1 times the omega ij, and so what we'll end up with is at location ij phi omega at ij, and this contains a term which is this omega ij times here we have this first term here and times this term here, and of course plus all the other terms here. And then if we look at the location at a different grid cell, at the ij plus 1 grid cell, so we can write this down here as well, so omega I and j plus 1 again times this Poisson bracket, but now at a different location. What we'll end up with is an omega I j plus 1, and the term with omega I will be this term here, with the j minus 1 will become omega ij, and now this is multiplied by a different quantity here. Now we have, and so this term has come from the second term here, and now just shifted by I plus 1. And so what you can see here is that this is, here we have an omega ij, and omega ij plus 1, here omega ij plus 1, omega ij, but they're multiplied by different quantities. And so what you find is that these quantities which should cancel out don't in this model. And so what you can end up with is you can change omega, for example, and you'll change the weighting, because these quantities here are in principle different. And so by having a different vorticity field, you can change the conservation of entropy. And so in general, these terms don't balance, and this leads to breaking the conservation of entropy. Now Arakawa in the middle 60s, about 66, 67, published a paper where he showed that this lack of symmetry and lack of conservation led to numerical problems in turbulent simulations. That was particularly for atmospheric problems. But he developed a linear finite difference equation, which is still widely used also in plasmas, because it's simple to implement and it conserves entropy and the total sort of density or total vorticity. And this is done by essentially combining this expression we wrote down here, which is just using the cell, basically the cells to either side. So I have kind of a cell in the middle, omega ij, and you're using cells to the right and left and up and down. This is one way of writing these derivatives, but you can also use these points over here, these sort of corner cells. And so Arakawa method essentially combines derivatives along these diagonals with this form here, and weights the two, so you end up with three possible ways of writing this derivative. Arakawa combines them, and so that keeps the symmetry and keeps these conservation laws. So if you're implementing Poisson brackets, I highly recommend you look at at implementing this method.